Okay, good morning, all the participants. Next, this week, we are going to deliver a lectures on physics of ocean remote sensing and its applications. So, this is the first day session. In this session, next 2 hours, I am going to present the principles of remote sensing. So, in this one, what we are going to cover is the basics of the remote sensing. So, continuously, I will continue up to 2 hours. So, whatever the doubts you arise in your mind, just you note down, and at the last, you can type it in your YouTube thing. At the time, I will answer all these things. Okay. So, now we will move to the original session of the principles of remote sensing. So, my name is Dr. Srinivasa Rao, scientist working at ESSO-INCOIS. So, I am dealing with remote sensing products and applications. So now if you come to the remote sensing first, what we are going to discuss in these sessions. So satellite remote sensing. In the satellite remote sensing, the first everyone we know this one, satellite image acquisition. First it involves. So if you are seeing this one that in the image screen, so you are seeing so many satellites. Okay. So each satellite, every satellite, it records some information. What information it records is that related to the Earth. So once we receive the Earth information, we are performing the applications. Now, if you talk about the Earth applications, these we are classifying into 3 groups. First one is a land application, ocean application, and atmospheric application. So once we receive the information from the satellite, based on the what kind of information we received from the satellite, what kind of data is useful for land applications, and what kind of data is useful for the ocean applications, and what kind of data is useful for the atmospheric applications. Okay, so all these fundamentals we are going to cover in this one. Now this whole this one technology, launching of the satellites and getting information, and we are analyzing it and we are performing the application. In one shot, this one we are calling it as a remote sensing technology. So this course is designed basically for the beginners. Okay, so for an already experienced person, you can able to feel that refreshment. Okay, so that's why most of the things what we are going to cover is in mind of the beginners. So if we are going for first, what remote sensing? Okay, to understand what is remote sensing, you forget about the remote sensing. Okay, so first dictionary meaning of the remote sensing we are dividing into 2, remote plus sensing. So first is a sensing. What is sensing? Okay, in our daily life, every day we are using in a conversation with our friends, and if you want to comment somebody, you don't have sense. If you are using that word, you don't have sense. Most of the time people thinks it's an unparliamentary word, but it is not an unparliamentary word. Sensing means simply it's a getting information. So when we are using, just you recollect, when we are using that word, you don't have sense. So sensing means getting information. If you are explaining something to me, I am not unable to understand what you are explaining. That means you are continuously providing information to me, but I am unable to understand that information. Then you can give the comment that you don't have sense. Okay. Now, if you come to the remote sensing, if we are talking about the remote sensing is not a specialized subject. It is everybody's subject. In nowadays, in every field that remote sensing is involved. Remote sensing is nothing but a one tool. That's why you come out of that one is a specialized subject and all. After this one, you came to know this one. Okay. So now what is, I explained what is sensing. So now you have to understand what is remote sensing. If you come to the remote sensing, now if you see in the slide, we have 5 senses. Everyone we know. Out of these 5 senses, the first 3, these are our eye, ear and nose. These 3 are functioning based on the remote sensing, and taste and touch is only sensing. So what is the basic difference between first 3 and second 2? In a first 3 cases, without physical touch, we are getting the information. Now, for example, how our eye is working. Just you are sitting in front of the system, you are watching it, you are not touching anything in front of your items. Without touching that one, you can able to identify that is a monitor, keyboard, mouse, table, chair, and opposite to whatever the windows and all. So how we are sensing that information means how everyone we know our eye is light falls on a target, reflected light is coming to or reaching to our eye. Once the eye captures that energy, sends to the brain, our brain is analyzing. Based on that, we are identifying the opposite thing. Here, that information carrier is the light, is carrying some information. Similarly, if our backside things also reflects, but that light is not reaching our eye. That's why we are unable to see backside things. Okay. So that means without touching anything, we are getting the information. Similarly, how our ears are working. Just if you are sitting in a room, any vehicle is moving outside, you are not seeing that vehicle, you are not touching that vehicle, but based on the sound we can able to sense that is a two-wheeler or bus or auto or lorry or anything. Based on the sound we are sensing it. Similarly, that voice is also, somebody is talking outside, we are not seeing that person, we are not touching that person, but we are identifying what they are discussing it and who are the persons discussing. So that means here that the information carrier is the sound. Okay, sound due to molecular vibration, sound is reaching to our ears, we are sensing it. And now third one is the nose. Based on the smell, we are sensing. Here the information carrier is the molecules, so that's a wind carries some information that reaches it. If somebody is cooking in the kitchen, we are not seeing and we are not tasting. Without that one, based on the smell, we can able to sense what they are making it. That means in first three cases, without touching the target information, we are getting it. That is a remote sensing. Now, if we come to the taste, unless any item touches our tongue, we cannot feel the taste. Through touch, we are sensing anything. That is only sensing. Similarly, our skin. Somebody touches our skin, we are sensing it. Okay. So that these are the difference. This is the fundamental difference between the sensing and the remote sensing. That means our human body also functioning based on the remote sensing principles. Okay. Understand? Okay. Now we'll move for the satellite remote sensing. We are going for satellite remote sensing. Now, how the satellite remote sensing working is, how our eye is working. Similarly, satellite remote sensing also works. Only little bit difference is there. That difference later I will explain that one. Now, if you see this one textbook definition, what is remote sensing definition? If you want to write examination or definition. So, remote sensing is the science of acquiring information about the target without actually being in contact with it. This is the textbook definition. Previously, I explained is the normal discussion. Okay, now if you are seeing in this picture, first sunlight is incident on a different targets. These are the clouds, these are over the land, or these are buildings and plants. So after incident, this one, the red lines if you are seeing is a reflected light is going into the satellite. Okay, that one. So like our eye. Now if you are seeing the blue lines here there is no incident light, but still some light is going into the satellite. Now what is the difference between the red one and the blue lines? Clearly I will explain later part. Here just I am mentioning it here that yellow indicates the incoming radiation, that is the electromagnetic light, incoming light. This EMR is a reflected light. Reflection means direction, change of direction. Okay, and EMR, okay, emitted EMR means emission light takes place. How this emission takes place, later part we are going to discussion. Okay, so now if you see this one, satellite means regularly we are using that word satellite. Okay, everyone. Now here you have to understand the two words, difference between the two words. In remote sensing, if you are taking any textbook, you are hearing two words. One is the satellite and sensor. You should understand, as a beginner, you should understand what is satellite and what is sensor. Now, the satellite means just you imagine our human body, assume as a satellite. Okay. So, our human body carrying different sensors. What are those sensors? Our eyes, ears, nose. These are the sensors. So now that means satellite is nothing but a one vehicle. That's all. If we are designed one satellite, we can place it number of sensors on one satellite. Okay. So how our body carrying different sensors. If you see this one, our eye capturing information is different, ears capturing information is different, nose capturing information is different. All information finally it goes into the brain. Our brain is analyzing and performing the application. Similarly, if you are designed one satellite, over that one, we can place 5 to 10 sensors, different sensors. So each sensor capturing information from where that information is coming from the earth. Okay, whatever the information comes from the earth, either it may be reflection or emission. Finally, the sensors captures those one. Each sensor captures a different information. All the information it sends back to the ground. We are receiving it and we are analyzing. We are performing the earth applications. Already I mentioned earth application means land, ocean, and atmosphere. Okay. I hope everyone understood what is the satellite and sensor. Okay. Now, we designed a satellite. One satellite, over that one, we placed the sensors. Next stage comes into picture is the launching of the satellite. Okay, where we are keeping our satellite. Now, today, the present scenario of our space, if you are looking, is this one, like this. Each dot represents one satellite. This shows the importance of the satellites. Okay. So in this one, different kinds of satellites are there. Those things we are going to discuss it. Okay. For your just to visualize purpose, I presented here this one. Okay. Now, after we designed a satellite, over that one we kept placed sensors. Next stage comes is the launching of the satellite. That means where we are going to place the satellite, and particular some height we are going to place the orbit. Okay. Generally, we have the two options. Either we are going to place our satellite in a geostationary orbit, and second one is the polar orbit. Why these two orbits? Why not one orbit? That is the fundamental question. Okay. So why we need two orbits? Okay. Later I will explain this one. Okay. Just first, everyone should understand what is orbit. Orbit means it's a once if I place my satellite at particular height, throughout its lifespan around the earth, okay, it rotates on particular orbit, okay, a particular path. So that path is nothing but a orbit. For example, in your room, okay, surrounded by your room, so one person is continuously, it's in a fixed path, it is rotating around your building. Okay, we can call it as that path, we can call it as a orbit. That particular person, we can call it as a satellite. And what that eyes, ears, and nose, these we can call it as a sensors. Okay, that is the one. Now, if we come to the geostationary, what is the difference between geostationary orbit and polar orbit? The first difference between the geostationary orbit and polar orbit is the orientation. Now, if you are seeing this orientation, geostationary orbit orientation is parallel to the equator. I am not going to explain what is equator. Okay, everyone knows that one. Okay, so this is the parallel to the equator. Okay, geostationary. And if we come to the polar orbit, perpendicular to the equator. Okay, so why we are calling it as a polar orbit? With the orientation is north pole to south pole to north pole. Okay, that's why we are naming it as a polar orbit. Later we are. This is the basic difference. And second difference, the first one is the orientation difference, and the second one is the height. If you are seeing that geostationary orbit, height of the geostationary orbit at 36,000 kilometer height, that is the fixed height. Why we fixed that height? Later I will explain that one. But here that understand 36,000 kilometer height, geostationary. And if you come to the polar, it varies from 700 to 800 kilometers. Nowadays, some of the satellites we are launching say 600 to 800 kilometers. So these are the second difference is the height. But if you come to the polar orbit, it's not a fixed height. It is a variable height. It varies from 600 to say 800 kilometers. This is the second difference, height. The first one, geostationary case, height is fixed 36,000 kilometers. And polar case, it's not a fixed height, it's a variable height. This is the second difference. Okay. Now we will go for details. Geostationary orbits. Okay. Why we are calling it as a geostationary? Geo means earth. Stationary means it's not at all moving, fixed. Okay. Orbit. That means if you place our satellite at 36,000 kilometer height, so what we feel is we feel satellite is not at all moving. As a satellite, from the satellite, if we are seeing our Earth, we feel Earth is not at all moving. That means not physically we are also feel Earth is not moving. We are feel we are stationary. But in a real world, we are not stationary. Earth is rotating on its own axis, and at how much time it takes one rotation around the one rotation, it takes 24 hours time. Due to that one only, we are observing day and nights. Okay, so in a real world, Earth is rotating on its own axis, is rotating 24, and that movement of the Earth, if you are seen west to east to west movement. Similarly, if we place our satellites in a polar orbit, now if you see this one, the satellite movement also west to east to west. So why we are calling it as a geostationary? The speed of the Earth and the speed of the satellite both are same. Okay, how we achieved this one 36,000 kilometer? I am not going into that, but Kepler laws explains this one. Okay, second Kepler law explains this one. If anyone interested, just you go through that Kepler laws in physics. Okay, so this is the one. Once if I what kind of okay. So what kind of satellites we are placing it in a geostationary orbit? That is the goal. Normally we are placing in a two kinds of satellites. One is the weather satellites, and second one is the communication satellites. Now, if you are seeing the weather satellites, what is the purpose of weather satellites is, now if you come to this figure, okay, so if after launching this my satellite at geostationary, so if I focus my particular interested area over the Earth, throughout its lifespan, my sensor looks that particular location. Continuously it looking at particular location. How it is possible is same a real world example I will give you. If two buses are moving parallelly with the same speed, we are seeing opposite person seeing us. We feel we are not at all moving. We feel both are stationary. But in the real world, two buses are moving at same speed. Similar concept will work here. So at particular height, if you are seen through the sensor, we feel Earth is not at all moving, but physically it is moving. Okay, so once these two speeds are equal at particular, why we are placing here in a weather satellites? Now if you come to this one, okay, this is the one example I am giving you. This is our Indian satellite INSAT 3D. Okay, so this height is this one around nearly. Okay, this orbit is the movement, this geostationary orbit. Now if you are seeing this one particular day, this is I am going to monitor the cyclone. Okay, so if you see the cyclone, my sensor is looking that particular complete area. So you see this one continuously, it is looking that one. Now we can monitor this one. Now you can able to see that one. If you have seen that one, India it fixed that cloud cyclone movement, you can able to see it. And again, I am doing it that animation. Okay, so that means once if I focus my sensor at particular region continuously, okay, why we need to monitor that continuously that one clouds? Okay, so weather satellite means first purpose of weather satellites is that to monitor the clouds. If you are seeing the cloud, especially in a tropical region, so clouds are not stationary, it's a dynamic. If you are seeing one cloud, next question comes in our mind is in which direction the clouds are moving. Is it going to give rainfall or not? If it is giving rainfall, how much rainfall we are receiving? Is it going to create a floods or not? All these things, if you want to answer continuously, we have to monitor that one. Okay, so we have the option of getting the information every minute by minute. We can get that one through geostationary, but normally we won't take that every minute by minute. If you, during the monsoon time, now this is the monsoon time. During the monsoon time, every 3 hours we are taking. Okay, if a summer season, that atmosphere is very calm, every 6 hours we are taking. Monsoon time, everything, because clouds will come to monitor the clouds. If any cyclone happened in the ocean, okay, every 1 hour we are taking. If cyclone landfall takes place, during that time, every 10 minutes we can able to capture that information. Okay, based on our requirement. Okay, so why these times comes into picture means, okay, so why not we are taking this one is the, so the satellite, sensor, all these are the electronic devices. Okay, so to function, to perform this all operations before launching itself, we are keeping that one battery attached with solar panels. Daytime, solar panels takes that sunlight and charges produces, the battery charges, and night time we are utilizing discharging, discharging. After some time the battery is losing the holding capacity of the power. If battery is losing that holding capacity of the power, no sensors and satellites won't function at all. Then we are going to announce that one decommissioning of the sensor. So that's why again we have to launch another satellite. That's why optimum utilization of the power comes into the picture. So optimally we are utilizing the power. That's why all these times comes into the picture. Okay. So this is the weather satellites. Now if you come to the communication satellites, okay. So if you see that communication satellites, different communication things are there. So out of this one, what I am going to, everyone knows this nowadays, this is a DTH service. We are using this one. Okay. So if you are living in an apartment, your top roof of the apartment, if you are seeing in India or any country, so different brands of DTH services are there. Okay, for example, in your apartment, 4 or 5 brands are there. If you carefully watch, each antenna's looking direction is little bit difference is there. So why the difference are? Each brand is using different satellites. Whoever comes to our home to install this service DTH, he knows in which direction their satellite is moving. He is focusing towards the satellite, and Earth is moving along the Earth, that our antenna is moving, satellite also moving. That's why we are continuously getting the signals. So if you want to disturb your neighbors, just you change the direction of the dish, they won't get the signal. Again, you have to help them, or the technician should come. Okay. So this is the communication satellites. Okay. So these are the advantages I explained to you. Okay, so some drawbacks also there. What is the drawback in a geostationary satellites? So weather satellite case, if you are seeing, if I place my satellite and focus in one particular area, throughout the lifespan, it looks only that particular location. But some group of people interested, no, I don't want to see that continuously one particular location. I'm sitting in this room, I want to see complete globe, what is happening. Then you have to place our satellite in a polar orbit. The polar orbit's orientation I already mentioned. That covers the North Pole to South Pole, South Pole to North Pole. Now this is the path of the Oceansat 2. This is our Indian satellite. Okay. So now if you come to the polar satellites, another way we are going to call it as a Earth observing satellites. Okay, that means complete globe we are going to cover with this polar satellite. How it is going to happen? Okay. So now if you see this one, this is the animation, you see this one. This is the polar orbit. Okay. So if once I place my satellite at polar orbit, the satellite is moving from north to south to north. My Earth is moving from west to east, east to west. So in this process, how it is going to cover complete globe, I will play a small animation from through that one. You can able to understand this is our Earth planet. So now if you see this one, the Earth is moving from west to east, east to west. The first time that satellite scanned the Indian region. Again, my satellite is moving in the same fixed path. Second time, it's scanning the adjacent portion. Again, my satellite is coming in the same path, orbit. Third time, it's scanning the further adjacent portion. Okay, here I am stopping it. Okay, now you see this one. My satellite, my polar satellite, first time it scanned this portion, second time this one, third time this one. Okay, so this one we are calling it as a first pass, second pass, third pass. Okay, you forget about why these gaps are coming. Okay, later part I will explain this one. Now just here you have to understand only the polar satellites one. Okay, so for your understanding purpose, again I am just, you can make out. The Earth is moving from west to east. How it is possible to cover complete globe? The satellite from north to south. This one we are calling it as a descending pass. If some satellites come south to north, we are calling it as ascending pass. The second time your descent portion. Third time further a descent portion. Okay. So Now, okay, here I am going to introduce another technical word. What is the here? Like this, it is going to cover complete globe. Okay, whatever you are seeing in this animation, this is the sensor of Modi's sensor. So that specification, if you are seeing that Modi's sensor, that one technical word, just you note down Swath, S-W-A-T-H, S-W-A-T-H. Later I am going to explain this one. Okay, Swath. So what is the Swath means? The distance between this end to this end, we are going to call it as a Swath. Okay. So if Swath is more, it takes to cover complete globe, lesser time. If swath is narrow, it takes more time to cover complete globe. Okay. Now, if you are seeing this one, Modi sensor with 2,300 kilometers swath, within the 12 hours, it is going to cover complete globe. So that means within the 24 hours time, one time it is giving a daytime, it covers complete globe, and a night time it is going to cover complete globe. Okay. So that is the one. If swath is narrow, it takes 2 days, some sensors 5 days, some sensors 15 days, like that. Satellite depends upon the swath. Okay, that's like this. It is going to. Now another most important point is whoever is going to work with the ocean data. Okay, so first any satellite, the first it is going to cover the Bay of Bengal. Why means the Earth is moving from west to east. So first it is going to cover Bay of Bengal, and second pass it is going to cover the Arabian Sea. That is the one. Okay, these are the one. Next third, like that you can able to see it. Okay, so this is the concept of the polar satellites. If you come to this presentation, okay. So now this polar satellites, okay. So in this animation, what I shown is exactly overhead to the North Pole to South Pole, South Pole. But normally polar satellites, we are keeping it as some inclination. Okay, if satellites in a polar orbit do not overpass, if the 20 to 30 degrees inclination also, we are calling it as a polar orbits. And how much time it takes to take one rotation is here, okay, is approximately 100 minutes. That means first it is scanning this portion, and again the time gap between the first pass and second pass is the 100 minutes time. That means, so if you are working with ocean data, okay, so the first pass and second pass time gap is the 1.5 hour time gap is there, and first pass and third pass, okay, 3 hours time. That is 100 minutes. Generally, we are talking about 1.5 hour, okay, or strictly speaking, 100 minutes. Okay, the time gap between first and second pass is the 100 minutes. That means any polar satellite to take one rotation, it takes 100 minutes time. That is the one. Okay, so now this is the one. And another time, if you are talking about the polar satellites, another word comes into the picture is the sun-synchronous orbits. Okay, what is the sun-synchronous means is a particular kind of polar orbit. Satellites in sun-synchronous traveling over the polar region, and the sun-synchronous synchronizes with the sun. That means always a satellite, it scans the portion wherever the sunlight falls on the sun. It's a local time. With respect to sun, wherever that sunlight falls on the earth, that particular region only it is scanning. Okay. Okay. The satellite in sun synchronous orbit usually to an altitude of 600. This is a polar satellite. Will be traveling at a speed of approximately the speed of the satellite 7.5 kilometers per second. Okay. With that 7.5 kilometers per second speed, within the 100 minutes, it covers one rotation. This is the one. Okay, sun synchronous means wherever the sun illumination takes, that particular region only it is scanning. Okay, this is about the polar satellite. Like this, in a polar satellites, we are going to cover complete Earth. Okay, so if Indian scenario, if we consider, so if any satellite during the launching time, we are hearing two words, PSLV and GSLV. So what is PSLV means? Polar Satellite Launching Vehicle. That means using the polar satellite, we are going to place satellite in a polar orbit. It may be varies, that height varies from 600 to 700 kilometers. That satellite is going to cover, that is a Earth observing satellites. If India is using GSLV, Geosynchronous Satellite Launching Vehicle, that means India is going to place satellite at 36,000 kilometer height. Either it may be a weather satellite or communication satellite. Like that, we can able to understand. Okay. So this is the regarding the orbits. Why some satellites in polar? Why some satellites in geostationary? In short, okay. So this one, this is the swath. Okay, already I explained this one. Okay. So why these gaps are coming is that when in this particular sensor case is the Modi sensor case, the gaps are coming. So, but if you are seeing a different satellites case, now this is the Modi's, these are the gaps. How these gaps we are going to fill this one is Modi sensor placed on a two satellites. What are those satellites? Terra and Aqua. Terra scans morning that around local equator crossing time is the 10:30 hours. Okay, and Aqua crossing equatorial time is the 1:30 hours. Okay, so whatever the sensor is the same, but satellites is different. Okay, that's why morning Terra is going to cover the Earth like this. These gaps, whatever the Aqua around 1:30, it is going to cover overlap all these gaps. Finally, we are going to get the complete without gaps. This one. Now, if you come to the very latest one, this VIRS sensor one. Okay, so if you are seeing this VIRS, compare with this Modi's VIRS sensor, the Swath is this is a 2,300 kilometers. This is a 3,000 kilometers. With this wide swath, overlaps are there. So that's why we won't find any gap here. Okay, if you are seeing MISR, this is a very narrow swath. The swaths will be like this. This is the first pass, this is second pass, this is third. But how the gaps will fill? Next day, all this comes in these gaps filling. Okay, it's now the Calypso, another satellite. These are the paths. Okay, these are the narrow satellite, not narrow swaths. Okay, these are the different swaths. Now, okay, along the swath, whatever we are getting the image. Okay, so it looks like we are calling it as a digital image. Why we are calling it as a digital image means any image you take it. Image we are calling it as a image or picture. Picture means it's a combination of array of pixels. If you zoom this particular area, you can able to see that pixels level. Okay, so for your understanding purpose, I am opening another one image. Okay, you can able to see it, that one. How that image. So this is the satellite picture. Just I am zooming it. If I am zooming it, sorry, I'm zoom out. Zooming. Okay, pixels. Okay, so now what it contains, that pixels is whatever the energy reflected or emitted from the ground. Okay, it's captured, that energy sensor capture that energy converts into a numbers. That light energy converts into a numbers. Each pixel stores some numbers. Those numbers we are calling it as a DN numbers. How the DN numbers are coming later I am going to explain. Just if you are seeing the values here, 86, okay, this one 91, this one 89, this one, okay, all pixels are same. So now if we come to here, so 128, okay, all this DN value depends upon the how much energy reflected from the ground. Okay, so this is the DN numbers. Just briefly I am giving. Later we will go one by one. So this is the DN numbers image. Okay, how this one is the electromagnetic energy reflection and emission. Now, if we are talking about the electromagnetic energy, we are okay. So this is the in a satellite remote sensing case, electromagnetic energy is the information carrier. So that's why we should know each and everything of the what is electromagnetic energy and what are the units and all these things thoroughly. We have to discuss this one. Okay. So now we are moving into now in the nature. So many energy in a different forms are there. Thermal heat energy, light energy, and nuclear energy, chemical energy, mechanical and electrical and sound. So out of all these things, in a satellite remote sensing case, we are using only light. Already in a ground, okay, I mentioned our ears also is nothing but a remote sensing. Okay, so by in a ears case is sound. Why we are not using that sound in a satellite remote sensing? That is the fundamental thing. Why we are using only the light? Okay, to understand that one, we have to understand the some concept. In the nature, any energy travels from one place to another place in a three mechanisms. What are those three mechanisms? Energy transferred from one place to another place is the first one is the conduction, second one is the convection, third one is the radiation. So now you have to understand everyone should understand what is the conduction, convection and radiation. Okay, to understand this one, next slide, you see this one. What is conduction? Conduction means heat. Okay, just if you consider this is a one iron bar, we are supplying energy at this end. Slowly the energy transfer this end to this end. How the transfer takes place? No? Due to molecular vibration. That means the first molecule, if you are supplying energy here, that heat, the first molecule takes that energy, it vibrates. So due to this vibration, it transfers energy from first molecule to second molecule. After that, the first molecule comes to the original state. And second molecule will vibrate and transfer to energy to third molecule while it comes to the normal state. Okay. So if it is not coming to the original position, we can able to see the change of the shape. Okay. Just like we are heating it. Okay. How this changing is of this one. Okay. So if in original shape exists, means the particle should come at that point. So that means heat transfers from one end to an end due to the molecular vibration is nothing but a conduction. That means here that medium is required to transfer energy from one end to another hand. Okay, here there is no physical movement, just only vibration of the molecules. Now if you come to the convection, second case, here that best example is the boiling of water. So during the boiling of water, just if you are supplying energy at the bottom molecule takes that water molecule takes that energy and the density become lesser one. Once the density becomes less, the molecule directly carries energy to the surface. That's why if you are boiling water, the first warmness you feel in the top layer. Later part only slowly it goes down. Okay. Bottom, if you touch that one, you won't feel that warmness. So this is one. That means here the physical movement takes place in between the molecules. The from bottom molecule picks that energy and it comes to the surface. Again, that bottom molecule it comes. That due to the physical movement of the molecules, if energy transfers from one place to another place, we are going to call it as a convection. So in this case also medium is required. If you come to the radiation means radiant energy, the transfer of energy from one place to another place without any medium support. If any energy transfers from one place to another place without any medium support, we can call it as a radiation. That means only one energy form is having that one is a radiation property, is the light. Light only can able to travel without any medium support. Similarly, if you take the sound, if you want to carry sound, some information one place to another, medium is required. So that's why we are in a satellite remote sensing case, we are using only light for remote sensing. So where we are placing the satellites at from out of the atmosphere, we are placing from 600 to 800 kilometers or geostationary 36,000 kilometer height. So at that height, there is no medium at all. If you are using sound for satellite remote sensing, it travels up to the troposphere where up to it reaches. After that, it is unable to reach from the satellite. But light without any medium support, light only can travel and it carries information and up to the sensor level and it records that sensor and that information sends back. That's why we are using light. Wherever now onwards, anywhere if you hear that word radiation, that means we are going to discuss about the light. That's all. Okay. So medium is not required because that's why the sunlight, how it comes to the earth is through radiation process without any medium support. That's all. Okay. Now I hope everyone understands that conduction, molecular vibration, there is no physical movement of molecules. Convection, most of the, if you are studying about the atmosphere and ocean science, convection, regularly we are hearing this word. Mixing takes place, the convective mixing. Okay. And advection means it's a horizontal movement. All these things, convection means that physical movement of the heat, that water molecules carrying some heat. Okay. The transfer one place to another place. That is a convective mechanism. Radiation means without any mechanism, without any medium support, that light can travel one place to another place. That one. Okay. Now, if you know the radiation, now that's why now if we come to that one, that energy, normally we are light. Another name of light is a technical, general name is the light. is a technical name is the electromagnetic energy. What is this electromagnetic energy? Later will come. And another name is the electromagnetic radiation. Electromagnetic radiation, EMR, in a short form we are calling electromagnetic radiation. Why means that radiation we are calling it as a without any medium support, energy is traveling one place to another place. That is it. Now if you come to what is electromagnetic, if you want to produce light, so in a childhood or intermediate level we are studying it. I'm not going into the electric field and magnetic field. Both should be act as a perpendicular. So this electric field and magnetic field acting perpendicular as shown in this figure, we can able to produce light. Okay, that much we'll discuss it here. We'll stop it. Okay, so now, okay, this is the light. Now, if we are calling it as a light, is an energy. So we should quantify how much energy we are capturing through sensor. Okay, how much energy emitting from the earth, how much energy falling on the earth, how much energy is reflecting. Everything we should quantify it, that one. To quantify that light energy, different theories proposed this one. One theory is the Planck's proposed one theory, quantum theory and Planck's assumption. And this light travels from one place to another place in two ways. One is the waveform and second one is the packets of energy in a particle nature. Okay. So that the energy travels from one place to another place in the form of the quanta, means one packet of energy in the terms of, okay. So if one packet of energy, we are calling it as a quanta, okay. So how we can quantify? Simple that equation, if you are seeing this one, everyone we know, E is equal to h nu. This is the energy, okay, quantification. E is the energy, packet of energy, and h is nothing but a constant. This one we are calling it as a Planck's constant, and nu is nothing but a frequency, okay. So what is a frequency? At this case, during that time I will explain. That means the constant, if you remove this constant in this equation, energy is proportional to the frequency. H is nothing but a 6.626 into 10 to the power of minus 34 joule second. Okay, this is some constant. Okay, later also in detail we are discussing that one. Now if you come to this one in terms of frequency, now that frequency, we can able to convert this frequency into, okay, another equation is there, frequency equal to c by lambda. What is c? Is nothing but a velocity of the light. That is also a fixed one. What is that one? Is the 3 into 10 to the power of 8 meters per second. That is also light of the energy also, it's speed of the light also is fixed. Constant. If you remove that constant, c, frequency is inversely proportional to wavelength. So what is wavelength also later I will explain. Just to watch it or note down this one. So nu is frequency and wavelength. Okay, c is the speed of. Now in place of nu, if you substitute 1 by lambda in this equation, how this equation turns to the E is inversely proportional to the wavelength. Okay, here the conversion in place of nu, you keep it here hc by lambda. Okay, hc both are constants. That's why energy is inversely proportional to the wavelength. That means if you are talking about electromagnetic radiation or light, okay, light energy, two ways we are representing that one. One is in the form of wavelength or in the form of frequency. These two we are representing. That units also we are representing sometimes in a wavelength units, sometimes in a frequency units. Okay. Now to understand this one, first everyone should understand what is wavelength and what is frequency. That we have to understand. Later part that relations will come. Now if you are seeing here, three waves we are seeing. Now this wave means from here to here up to here, we are calling it as a one wave. This is the second wave. So total here you are seeing a 2.5 waves. So up to here, okay, this combination of one trough and this one, okay, lobe, okay, this one is the one, sorry, okay, one wave, okay. So So the distance between this one here to here, we are calling it as a wavelength. Okay, this one wave, that length of this one is the wavelength. Okay, so the here to here also same wavelength. Okay, so now if we come to here, how many waves are there? From here to here is the one wave, here to here is the second wave, here to here is the third wave, here to here is the four waves. Four waves are there. Here at this wavelength, four and a half waves we are seeing. Here same way, here a wavelength also, distance between here to here we are calling it as a wavelength. Now if we come to here, wavelength is more. Okay, here the wave is up to here. Okay, one turn. Okay, so here to here, one wave. Now if you see this one, it's compared to 3. In this case, wavelength is more. Here is a moderate, middle. Here is the less one. Okay. So now these are the wavelengths. Now if you see this one, okay, now the second one is the wavelength is this one. Now if we come to the frequency, how we can able to define that one? Frequency, just from this particular, just if we consider this is one particular point. From this particular point, within the 1 second time, how many number of waves crossing that particular point? Okay, how many number of waves crosses that particular point? For example, at this point, within the 1 second, 10 waves crosses. That frequency is 10. Units are hertz. Okay, so within the 1 second, 100 waves crosses, 100 hertz. 200 waves crosses. That unit is frequency is the 200. That means within the 1 second time, how many number of waves crosses that particular point? So when more number of waves crosses, okay, if wavelength is short, that means it's less. Within the short time, more number of waves crosses. If wavelength increases, okay, so less number of waves crosses within the 1 second of time. Okay, so that means, okay, one wave you consider as a one packet of energy. Now if you see this one, in this case, within the 1 second of time, less number of packets crosses. Why means wavelength is more. Wavelength units is the nanometers or micrometers. In terms of length means it's a meters. Okay, so now if wavelength is more, within the 1 second of time, less number of waves, that means less number of packets, energy packets crossing. That's why this energy is less. That's why this relation, if you are seeing, if wavelength increases, less number of waves crosses that particular point, energy decreases. If we come to here, wavelength reduces, less. If wavelength is less from particular this point, within the same 1 second of time, more number of waves crosses. More number of waves means more number of packets crossing. More number of packets means more energy is that one. That's why this is the proportional relation. So, okay, frequency. I hope everyone understand this one. Okay. So now based on this one only, if you take any textbook remote sensing, that units, if you are seeing light, in terms of either we are representing in terms of a wavelength, that is a micrometers or nanometers, or in terms of a frequency. Okay, that gigahertz and kilohertz and hertz we are there. Okay, I hope everyone understands that relation. Based on this, if you understand this relation, remote sensing is very easy. You can, okay, and normally if you in our regular time we are hearing the two words, short wave and long wave radiation. Short wave radiation and long wave radiation. Short wave radiation means that wavelength is short. If wavelength is short, more number of waves crosses, and that means it carries more energy. Okay, long wave radiation, that wavelength is long. Wavelength is long means it's a less energy it carries. That's all. Okay, that is in fundamental here. Okay, understand this relation. Now, if you see this one, total electromagnetic energy, different wavelengths combination. Okay, different wavelength. Okay, light. Okay, if you take light, so different wavelengths. It represents in a different names. How we are classifying this electromagnetic radiation? If you see, that starts with, this is all wavelengths, gamma rays, X-rays, ultraviolet rays, and the small portion we are calling it as a visible light. And after that, infrared rays, radar radiation, these are the microwaves. Later we will go into that one. So out of this wide spectrum of light, so one small portion is there, that portion of the light 400 to 700 nanometers. That we are calling it as a visible light. Why visible light means? So in this region 400 to 700 nanometers, our eye is sensitive. So below 400 nanometers and above 700 nanometer, even though that light carrying that information comes to our eye is not unable to that sensitive that light. That's why we are unable to capture that information. So our eyes are sensitive only for 400 to 700 nanometer. That in the first slide I mentioned. So what is the difference between sensor and our eye? Is a satellite sensor. Okay, our eye is sensitive for only 400 to 700 nanometer, but satellite sensor is a mechanical device. That's why it can able to capture any kind of wavelengths, all kinds of wavelengths, whatever the required wavelengths. We need all that light it captures and it gives back to us. Okay, that is the difference. All kinds of lights it can able to capture. Okay, that is the difference between our eye and satellite sensor. Okay, so if we are talking about visible light, we can able to see that colors. Okay, that's why colors we are able to see that colors, blue light. Okay, so now if you are seeing that one, our visible light, we can able to classify into 3 groups. 400 to 500 nanometers, we can call it as a blue light. 500 to 600 nanometers, green light. Okay, 600 to 700, red light. These blue, green, red, these are the primary colors. All remaining colors are the combination of these 3 primary colors only. Okay, but now if you are seeing this one in the blue region, different colors are there. How the colors are coming is different wavelengths. If it is a 400, this color, 450, blue color, this color, 500, green color, 520, different green color. Okay, just a 580 or 590, yellow color. Okay, 600, just a starting of the red. 700, this one. Above 700, we are calling it as the infrared. Okay, so each wavelength, okay, how much energy is carrying, we know E is equal to H nu. If you know the wavelength, you can substitute in that one H constant, substitute it, you can able to measure packet of energy. Okay, that's all. Similarly, if you know the frequency, substitute it, you can able to derive it. E is equal to H nu and Hc by lambda. That's all. Now, if you see the table form, electromagnetic energy. Okay, so this one is the electromagnetic radiation, solar radiation, commonly classified on the basis of the radiation wavelength. Radiation means already I mentioned. Okay, don't confuse it. Light, that's all. Wavelength into a several regions or bands. Okay, so now if it is in a gamma rays, one name we kept it. So if wavelength is less than 0.03 nanometers, we are calling it as a gamma rays. So if once the gamma rays enters into the atmosphere, completely absorbed by the upper atmosphere. Okay, whatever the gamma rays coming from the sun, okay, absorbed by the top of the atmosphere, it's not reaching to the ground. Okay, if wavelength is less, it contains more energy. So that is all. Now X-rays, second group. Okay, so 0.0232 to 3, we are calling it as a completely absorbed by the upper atmosphere. Okay, these also won't reach to our ground. Ultraviolet B, 3 to 300 nanometers, completely absorbed by the atmospheric gases. Okay, oxygen, nitrogen, O3, ozone, okay, upper atmosphere. Ultraviolet A, 300 to 400 nanometers, transmitted through the atmosphere, but atmospheric scattering is severe. That means ultraviolet rays, if it comes to the A, 300 to 400, transmitted through the atmosphere, it is transmitting, and atmospheric scattering is severe. What is this scattering? Later I am going to explain this one. Okay, just to listen that word scattering. One new term came. Visible light. Next classification is visible light. 400 to 700 nanometer, transmitted to the atmosphere with moderate atmospheric scattering of the shorter waves. So within this 400 to 700 nanometer, so atmospheric influence is less, but scattering is, some effect is there. Where that atmospheric scattering is severe, at shorter wavelengths. Shorter wavelengths means near to the 400. Longer wavelengths means near to the 700. That means at blue light, atmospheric scattering effect is there. Compare with green and red light, because wavelength increases. Okay. Similarly, next one is the reflected ion. 700 to 3000. Mostly reflected radiation. So that means reflected radiation means light. Okay. So the atmospheric influence is less. Now thermal ion, 3000 to 14,000. Absorption of a specific wave. That means atmospheric influence is less. Only that absorption takes place at CO2, O3 and water vapor. Okay, little bit atmospheric influence. Now if we come to the microwave, 1 millimeter to 1 meter wavelength. This one we are calling the microwave. Over this microwave, atmospheric influence is very less, almost negligible. Little bit is there. That means if you are using the microwave, atmospheric influence is less. This is based on this. That means finally, if you are seeing in this table, if wavelength increases, atmospheric influence is minimizing. In the shorter wavelengths, atmospheric influence is high. Longer wavelength, atmospheric influence is less. That's all. Okay, this is the one. Now, if you see this one, now this slide is most important one. So if you need that screen capture also, you can take it. So now if you take any remote sensing book, these words will come into the picture. Okay. What are those? Radiant energy, radiant flux, irradiance, radiant intensity, radiance. Okay. So spectral radiance. If you understand this one, it's very easy. I will explain this one. If you understand this one, if you take any remote sensing book or during the remote sensing applications time, the energy quantification time, all these terms will come into picture. It's very easy. Now the first one is the radiant energy. This radiant energy description is nothing but already I mentioned one packet of energy. That one we are calling it as a quanta. So one packet of energy, that unit is the joule. That's all. Okay, it's a joule. One packet of energy, that unit is the joule. That one we are calling it as a radiant energy. Now second one is the radiant flux. Okay. So the flux means unit, if you see this one, joule per second. That means in terms of joule per second is nothing but we are representing as a watt. How we'll define is the energy per unit time. That means unit time means 1 second. Within the 1 second, how many packets are incident on the target or how many packets leaving from the target? Either incident or leaving, both. Okay, within the 1 second, how many number of packets? That one we are calling it as a radiant flux. So, for example, watts. Okay, within the 1 second, 20 packets are leaving from the target. We are calling it as a 20 watts. Within the 1 second, 100 packets crosses. That we are calling it as a 100 watts. Okay, that one we are calling it as a radiant flux, energy per unit time. Now, if we come to the irradiance, that symbol we are calling it as a E. Irradiance means just if you see that unit, watt per meter square. So if you are seeing this one, in place of watt, if you put joule per second per meter square. Meter square is unit for area. Okay. In this case, within the 1 second at one particular point, how many packets are incident or how many packets are leaving? Now, if we come to the irradiance, within the 1 square meter area, within the 1 square meter area, within the 1 second of time, how many packets are incident or how many packets are leaving? That means if you are taking 1 square meter area, so within the 360 degrees, how many packets of energy is incident at particular place and how many packets of energy is leaving? Okay, now if you see this one radiant flux, this is the bulb example you see. In all directions it is going energy within the 1 second. Here that irradiance. So area we are taking. So within that particular area, how much energy is falling? That is nothing but a irradiance. Now if we come to the radiant intensity. Radiant intensity means watt per instead of meter square, steradian in one particular direction. Steradian is unit for the direction. So in one, okay, here in all directions, here one particular direction, watt per steradian means within the 1 second of time, one particular direction, how many packets of energy is leaving or how many packets of energy is incident. That is the radiant intensity, energy, okay, per unit time at certain solid angle. Okay. So now if we come to the radiance, radiance means watt per meter square per steradian. That means steradian. Okay, here what it came from. So again, that area is came. okay, and steradian. Watts per meter. From one square meter area, within the 1 second of time, how many number of packets are leaving in a one particular direction? Okay. So for more clarity, I can able to tell. For example, if you are sitting in this one, from your system or keyboard, from all 360 degrees, energy is falling. Just I am sitting here, okay? Over me, all 360 degrees energy is falling, and at the same time, all 360 degrees energy is reflecting. But thing is, so in front of me, 10 students are sitting in a different locations. So in this direction, person receives one kind of energy. This direction of a person receives one particular type of energy. This direction is this one. So that means, so if you consider all 360 degrees, we are going to call it as a radiance. So if you come to the radiance, so within the one particular direction only, that means whatever eye is capturing, one particular direction of energy only our eye is capturing. But in my body, all 360 degrees energy is falling. That we are calling it as a irradiance. Radiance means of one particular direction. That we are calling it as a radiance. Now, in a satellite remote sensing, we are calling it, in place of radiance, we are calling it as a spectral radiance. What is spectral radiance? Means up to my eye, all wavelength, visible light, 400 to 700 nanometer reached up to my eye. But thing is, if I wear one green glasses, what these green glasses will do? Green glasses will allow only green light, remaining blue light and red light, it is stopping it. So that means my eye captures only green light, if you are seeing in this diagram. Okay, up to blue light, green light comes to here. After this one, the glass, only green light only it allows. So that one, if one particular kind of wavelength if you are capturing, that one we are going to call it as a spectral radiance. That watt per meter square per steradian and micrometer. That means in a definition form, if you take, okay, within the 1 second of time, within particular 1 square meter area, in a one particular direction, at particular wavelength, how much energy we are capturing. That's all. Okay, understood? How many number of packets within a one particular second from one square meter area in a particular direction and particular wavelengths. That micrometer is a unit for wavelength. That one we are calling it as a spectral radiance. Okay. So these words, if you understand, always in a remote sensing case, most of the time we are using that word irradiance and radiance. Irradiance means from sunlight, whatever the sunlight falls on a ocean surface or earth or clouds. That one in all 360 degrees is incidenting. That one we are calling it as a irradiance, watt per meter square. If you introduce particular direction, we are calling it as a radiance. The relation between irradiance and radiance is the angle. Irradiance equal to some solid angle into that radiance. We can able to relate it to these two things. I hope everyone understood. Okay. So this is the one. Once if you clear all these things, satellite picture, whatever the DN value, how the DN value is coming, the sensor capturing energy is the spectral radiance. In a sensor, we are keeping different wavelength bands. Okay, later I will explain. So that particular interested wavelength only we are capturing. That's why we are calling it as a spectral radiance. Instead of radiance, we are. So radiance means a radiation process, light. That's all. Okay, clear? Okay, now these are all fundamentals. Okay, after that one, how much energy is releasing? Okay, at what wavelength it is coming? At what frequency it is coming? All this explains some radiation loss are there. Radiation loss means again it's a light. We are going to deal with light with some loss. Okay, before that discussing the radiation loss, that fundamental thing is object in a universe emits electromagnetic radiation according to its well understood radiation laws. Any substance, it may be solid, liquid or gas, emits radiation according to its absolute temperature. Okay, absolute temperature means in terms of Kelvin. Kelvin means 0 degrees centigrade. Normally we are using that centigrade. Plus 273, you can add this 273.15. It centigrade converts into a Kelvin. Okay, the ability to emit the radiation. That means in the nature, every body, okay, if any substance, it may be a solid or liquid gas, it has its own temperature. If it is having any temperature, so equivalent to the temperature, it emits some light. That is the concept. Okay. So now here the black body, one term will come in a radiation. Black body means it completely absorbs whatever the incident radiation, and at the same time it emits total radiation. So, but in the nature, no substance is pure black body. But normally in nature, we consider the sun and earth surfaces behaves approximately as a black body. Yeah, how the sunlight, whatever the energy it emits. Similarly, earth also. Okay, later I will explain this concept. Okay, so actually how we are calling it as the sun as a black body. Okay, sorry, sun and earth. Okay, this is the radiation loss. That means here in this slide, it is telling to us in the nature, any body is having the temperature that's 0 degrees centigrade. So, or it is a minus 273 degree Kelvin. If it is greater than minus 273 degrees Kelvin, in any body's temperature, okay, contains the temperature equivalent to that, it emits some radiation. Okay, so to explain this concept, that radiation loss, okay, so and after that, okay, to understand this slide, don't confuse it at all. Here it's very simple. I will simplify this one. Okay, so here I am representing in a energy, representing in a graph. Okay, so radiation emitted by, if any object emit electromagnetic radiation due to its temperature, that means it's a inherent, even our body also. Okay, now if you are seeing here, this is our body. Nowadays, after COVID, everywhere we are seeing one instrument is keeping over our head. It is giving our body temperature. How it is giving body temperature is based on our body temperature. Our body is emitting energy. So that emitted energy captured by that instrument and giving the temperatures. So I have fever. So my body temperature increases, more energy it emits. If more energy it emits, it reflects on the device, more temperature. If my cold, okay, less temperature. Now if you see here, this is the thermal picture of our human body. In our human body, we are measuring our body temperature. That means we are feeling our whole body is in the same temperature. But in a thermal scanning, if you see this one, whole our body is not in a uniform temperature. Wherever physical movements are there, here our brain, okay, this blue color, joints, wherever this one, it's a movement is there, it's a blue color. Blue color means again blue light, wavelength 400. That means it's a short wave. Short wave means energy is inversely proportional to the wavelength. That means if wavelength is short, more energy. So that's why wherever movement here, more temperatures. That's why at these places, only olden days, thermometers are keeping at this place. Now we are head temperatures. But the spinal cord, there is no movement at all. That's why it's a lesser temperatures are there. Similarly, if you see the cat, okay, thermal this one. Okay, now if you see this one, this body temperature, compare with our temperature, body temperature is very less. Okay. So that energy is this one. Okay, these are the different temperatures. Okay, now the same thing, if you bring it into this graph shade, that y-axis you see, this one is the flux. What is the flux? Means that again just unit is the watt, joules per second. Within the 1 second of time, how many packets of energy is leaving? Okay, so now if you see this one, if any targeted body temperature or substance temperature 18,000 kelvins. So the light comes in a blue region. Maximum energy emits at blue region. What is the blue region? 400 nanometers. If it is a yellow light, 6,000 degrees Kelvin, it emits light in a yellow color. What is that? Just it is in between 400 to 700 nanometers. Red light temperature 4,000 K is this one. Slowly now the flux is reducing, wavelength is increasing. That means wavelength increases, energy is decreasing. That's all. Okay, it is shifting this one. Now, if you see this one, a real example, what I will give you is, just if you are cooking anything on a gas stove, the flame color, if you are seeing, it's a blue color. That means why it is a blue color we are meeting means, it is a consumption of the gas is the same. If flame color is blue, it gives, within the short time, it gives more energy, more heat it gives. That's why quickly we can able to cook that items. So if that flame color turns instead of blue to yellow to red, then that means consumption of the gas is the same, but thing is giving energy is less. If giving energy is less means unnecessarily gas is wasting. That's why we have to take the servicing, that one. That burners we have to clean it. That's all. Okay. This is the relation between the wavelength and energy. So this relation, that flanks radiation, that flanks explained with one mathematical equation. So if non-mathematics people, non-physics people, don't worry, it looks like a complex thing. It's a very simple equation. I will simplify this one. Okay. So what this law is explaining, this one is energy is a function of wavelength and temperature. This is the relation. So it's explaining the relation between the temperature versus wavelength, and this equation is H, 2hc square by lambda to the power of 4 by e to the power of hc lambda kt minus 1. So in this equation, other than temperature T and wavelength lambda, all remaining are the constants. Okay. So H is a Planck's constant. The value is this much. Units are joule per second. Okay. One packet energy, joule second. And the temperature is 1.38 into 10 to the power of minus 20 joule per K. K is unit of the temperature. C, the speed of the light here. Okay. 3 into 10 to the power of 8 meter per second. If you substitute all these things, how? Okay, this law explains the relation between the wavelength and temperature. But now the wavelength and temperature, if you have seen that x-axis previously. Okay. So wavelength, okay, temperature increases, okay, temperature decreases, wavelength increases. This law explains this one, Planck's radiation law. And this looks like a little bit complex, okay, complicated. So that's why to simplify this one, Stephen Boltzmann's law, Boltzmann explains, simplified this equation. So that integration of Planck's law, this equation, if we take the integration, it's Boltzmann's law integrates Stephen Boltzmann's law. And if you take the differentiation, that of Planck's law, Wien's displacement law came into picture. These two laws are very simplified. In a remote sensing, we are using those two laws only. Now, if you see this one, Stephen Boltzmann, you forgot about this big equation. Okay, Stephen Boltzmann's law gives what? Relation is energy equal to some constant sigma into T to the power of 4. T is a temperature. That's all. Very simple. That means proportional relation. Energy versus temperature. Inverse relation. Okay. So E is the total amount of radiation, watts per meter square. Okay. I'm not elaborating every time. Watt per meter square. Okay. Rho. Okay. Sigma is a constant called the Stephen Boltzmann's law. That value is 5.67 into 10 to the power of minus 8 watt per meter square per Kelvin. T to the power of 4 means Kelvin to the power of 4. T is temperature in terms of Kelvins. Okay. Now, if you take the one best example to understand this one, sun. Sun temperature we are considering as 6000 kelvins. If the 6000 kelvins you substitute in this equation, the C equal to sigma value is this much, 5.67 10 to the power of minus 8 watt per meter square Kelvin, 6000 to the power of 4. If you solve this one, finally what we are getting, how much? 7.3 into 10 to the power of 7 watt per meter square. Okay, that means, okay, within every 1 second. Okay, so from the sun, how, if you consider on over the earth, 1 square meter area within the 1 second of time, how many number of packets are falling? Means 7.3 into 10 to the power of 7. It's a huge, big number. Okay, this much of energy, every square meter area over the earth from the sun, this much of energy is falling on the earth. Now, if you see that temperature of the earth, okay, 288 Kelvin. Then E equal to 5.67, the substitute, that final solve this one. Finally, it is giving the 390 watts per meter square. You see how much is incident, how much is emitting. Almost negligible. That means whatever the energy falls on the earth absorbs completely. That's why we are calling it as a more near to the black body. This one. Okay, now if you see based on this equation only, just one example I will give you. Solar. Nowadays, everywhere we are using solar technology. If you are seeing that solar panels, one side only we are keeping. Bottom side we are not keeping it. Why? Means whatever the sunlight, most of the energy comes from the sun. It's these many units. Okay. Okay, but from the earth, very less energy. If you are keeping bottom also, what is the use of that one? We won't get any electricity from that one. Okay, so this is the one example. That means what Stephen Boltzmann's law is explaining is based on the body temperature, how much energy is coming from the body. That energy we can able to measure it using the sensors. Okay, this is the Stephen Boltzmann's law. But thing is, to design the sensor, we should know the energy is coming, but whatever the energy is coming from the target based on the temperature, at what wavelength it is coming, if you know that one, we can able to design the sensor with some specific bandwidths. Okay, so to explain that one, what law is going to explain this one is here. This is the Wien's displacement law. He explains this one. So what is this Wien's displacement law is giving? Okay, energy. This law is explaining. If you know the temperature, how much energy is coming, it is explaining. But what the energy at what wavelength it is coming? If you want to quantify it, Wien's displacement law is explaining. Lambda max, that means maximum energy, is equal to 2897 by temperature. That's all. Very simple equation. Okay. Now, if you take this one, now it's the same thing. Hotter body emits most of their radiation. Okay, I repeat again. Okay. Now, if you see this one, same that the sun and earth, you apply it. 6000 K lambda max. Okay. 2897 by 6000. You will get the lambda max. Wavelength is 482 micrometers. So, micrometers, if you convert into nanometers, multiply with 1000. Okay. So, micrometers mean 10 to the power of minus 6, nanometer mean 10 to the power of minus 9. So, 482 nanometers. That means from the sun, with all wavelengths, sunlight is coming. Okay, wavelengths coming. But thing is, most of the radiation either absorbed or scattered in the atmosphere, but maximum energy reaching to earth at what wavelength means 482 nanometers, we are getting the maximum energy from the sun. This is the one. The same graph is like this. Yet, okay, 482 nanometers wavelength, maximum energy is reaching to the ground. So, after reaching from this one, if ground temperature, earth temperature 288 Kelvin, substitute. So, but earth emits that radiation at what wavelength is it? 10 micrometers. If you convert into nanometers, 10,000 nanometers. Okay, 10,000 nanometers means at that nanometer, our eyes are not sensitive. So that's why if daytime, sunlight falls, and if you see in the CC cameras, okay, if you see, okay, so daytime we are seeing the everything in a color pictures we are seeing. But in the same that CC cameras in a night time, that people looks like in a grayscale. So how that grayscales? Similarly, in a geographic, National Geographic channels, if you are seeing that forest, daytime tiger, if you are seeing, we can able to see that yellow and black lines. But in the same tiger, if night vision, if you are seeing that grayscale image only, it's why means in a daytime due to sunlight, whatever the light falls on a tiger, it reflects back. Nighttime, whatever the energy sends, that one is in terms of the thermal infrared. So that thermal infrared cameras, through thermal infrared only we can able to capture. Through our eyes we are unable to capture. That's why the 10 micrometers is not sensitive for our eye. That's why that our light is coming up to our eye, but our eye is not capturing. If eye can able to capture this also, simply through our eye we can able to measure the temperature of that any target. That instrument devices are not required. Just you look it like this, you can able to measure. Our brain can able to measure the temperatures of the target. But it's not sensitive. That's why it's not measuring just to visual light. Whatever the our opposite targets, whatever the light reflects. Okay. So in a visible light, that only we can able to see. Other things we are unable to see. So this law. So why we are calling it as a displacement? Simple. If temperature increases, the wavelength shifting takes place, displacing that one. So that's why we are calling it as a Wien's displacement law. Okay, I hope everyone understood. Okay, so now based on this law only, we are designing the sensors. If you want to measure the temperature of the sensor, first over the ground, we are measuring the temperature of the target, your interested target. At what temperature? If you know the temperature, you can able to calculate at what wavelength maximum energy is emission takes place. That particular wavelength bands, okay, that bandwidth. For example, if one of the from this mouse, so light reflects, okay, at 8 micrometers. So that means, okay, so if I want to perfectly capture this mouse through remote sensing, I can design my sensor, okay, plus or minus 20 nanometers or 30 nanometers or 50 nanometers, okay. So we'll take this maximum wavelength we are getting now. From that wavelength, na, plus or minus we are adding something, and we are considering that as a band or channel. Okay, we are designing like that. So like that we are designing that one. So this gives the energy. This is the wavelengths. Okay, understood? So okay, thermal remote sensing works based on this one only. I hope everyone understood. Okay. So now you understand that how the radiation is taking place and all these things. Okay. Now here that radiation once from the sun, if radiation comes into the atmosphere, okay. So after the crossing that ozone layer and nitrous oxide, carbon dioxide, and all top of the atmospheric gases, finally it is entering into the maximum wavelength what we discussed, that of 480 nanometers, that visible light. Okay, this light enters into the atmosphere. Okay, after entering the atmosphere, it is falls on a targets. So once it is incident on a target, three types of phenomena takes place. One is the first one is the absorption takes place, transmission takes place, and a reflection. That's all. Okay, three processes. What are the process next? Okay, so now this is the absorption symbol we are giving A. And okay, absorption means occur when a radiation is absorbed by the target. Transmission means it's transmitted through the target, and a reflection means a direction it changes, reflected back. Okay, where it is a reflection takes place. Now, if you see in this diagram, energy falls, incident, absorption, transmission, and a reflection. When this transmission takes place in a two cases, either it's a water body or glass, then only transmission takes place. Other than water body in nature on the earth, okay, all remaining are the non-transparent. Non-remaining means land, buildings, vacant land, vegetation, okay, hills, anything, okay, other than the water, remaining things are the only non-transparent material. If it is a non-transparent material, only two phenomena takes place: absorption and the reflection. That's all. Okay. Now, same thing if you put it in a mathematical form, total energy equal to absorption, transmission, and plus reflection. That's all. Okay. Now, this equation, if I divide into total incident energy, okay, total energy by total energy equal to 1. Absorption energy, how much energy is absorbed by how much energy is incident. Incident energy, already I mentioned, incident energy means irradiance. Okay, within the 1 second of time, within the 1 square meter area, how many packets of energy falling. Okay, total energy. Okay, absorption energy by total energy, transmission energy by total energy, reflected energy by total energy. Reflected means change of direction. Okay, this one is 1. Absorption energy by total energy, we are calling it as a absorbance, and transmitted energy by total energy is a transmittance. Reflected energy by total energy is a reflectance. Now in this equation, if it is a non-transparent, transmittance is 0. That means non-water bodies. Now the reflection, how the equation changes, if this is 0, reflection equal to 1 minus absorptance. Absorptance equal to 1 minus reflectance. That means what? But thing is, through our eye or through sensor, what we are capturing is So if any light falls on a target, reflected light only we are capturing. If it is reflected light is captured, now if you are seeing here at this portion, dark, here is the bright, here is the dark. It means in the nature, some of the targets, in a satellite picture, some of the targets looks like a dark, some of the pixels, okay, it looks like a bright targets, okay. So why some is dark and some is bright means based on the, here if you are seeing this one, particular wavelength region, whatever the materials at this location is, more absorption takes place. That means the first-hand information we are getting through satellite picture is the first-hand information. All these are the absorbed materials. These are the non-absorbed materials at this place. What are these target? Later we will analyze. First-hand information we are getting through remote sensing is the absorbed and non-absorbed material. So that means particular the same wavelength region, some targets acts as a absorption materials, some targets acts as a reflection material. Based on these properties, we can able to identify the where the absorbed materials are there. Okay, this is the one. So if you take that, this is water body. Water body is a transparency. All three phenomena acts this one. Always water body looks dark in satellite picture. Why means if it is a pure water body, that means whatever incident light, it penetrates into the water and very few, okay, only it reflects back. That reflected light is capturing that. That's why it looks like a dark. I hope everyone will understand this concept of first hand reflected materials and absorbed materials. Okay, that is a transparent water body. We are considering as a transparent, non-transparent. In a non-transparent material, two process: absorption and reflection. Transparent materials, absorption, reflection, and transmission. That's all. Okay. Hope during the ocean color remote sensing tomorrow. Okay. So during that time, transmission plays a crucial role. Okay, that's why during there we will discuss that one. Okay, now this is the target with the over the land, okay, over the earth. But thing is, after reflection from the target, okay, so once that means if once leaving the target, okay, that energy, okay, radiation, once it enters into the atmosphere, okay, what will happen is due to the atmospheric molecules means either gas molecules, dust molecules, and clouds. These three broad classification is air molecules, dust molecules, and clouds. Due to these three kinds of molecules, no? So the scattering takes place. That scattering, what is the difference between scattering and reflection? Reflection means incident light. After this one, the incident light, all light goes in a one particular direction. So it's a known direction. That we are calling it as a reflection. Scattering means all light scatters. That means all 360 degrees it scatters. Reflection means only one particular direction. That's all. Okay. So once it enters into this one, scattering takes place. So this absorption means complete absorption. That's all. Okay. So now the scattering mechanism, three kinds of atmospheric scattering we are noticing. What are those? One is the Rayleigh scattering, Mie scattering, and non-selective scattering. So what is once the whatever the energy from our target after emission or reflection, once it enters into the atmosphere, because from the target to the sensor level, the signal carrying some important information in a form of light or radiation. During this one, if our sensor captures a whole 100%, okay, 100 units reflected or emitted, whole 100 units if I can able to capture through my sensor, if atmosphere is not there, so whole 100 units reaches up to my sensor, then I can able to get the 100% accurate information about the target. But thing is, here in the atmosphere, scattering takes place. Because of the scattering, some of the energy, valuable information, we are losing it. That means 100 units reflects, okay, 20 or 30 units scatters. That means losing that one. That means 30% of information we are losing it. If 13% of 100% information we are not getting now, that's why we are unable to study the properly the target characteristics. Okay. Now the best example is there. In front of you, one person is standing. If it is nearby, or to 20 meters is there, you can able to see the perfect picture of the person. Who is that person also? So if that person in between, that during the hazy time, if atmosphere is hazy or it's raining, so we are seeing the person, but we are unable to see clarity of his face. Who is that person? We are unable to see. Even though he is standing in front of us in a 10 meters distance, during the fog days, we are unable to see perfectly. That means whatever the energy emitting or reflecting from the person is 100% not reaching to our eye. In the atmosphere, some of the energy due to the scattering of these molecules we are losing. That means we are losing some information. So now we have to understand, due to the air molecules, Rayleigh scattering takes place. Due to dust molecules, Mie scattering takes place. Due to clouds, non-selective scattering takes place. Now, if you see acting of the Rayleigh scattering, once the light falls on a molecule, air molecule, all 360 degrees, okay, forward, it goes the forward and backward also it comes, light. But in a Mie scattering, it falls on this one. Most of the light, okay, so it goes into the forward direction only, okay. So and another difference is in a Rayleigh scatter, forward direction it moves. Non-selective means in all 360 degrees and we don't know in which direction it is moving, okay. So that is the one. Now if clearly we discuss this one, Rayleigh scattering also, this slide don't confuse it, very simple. I will simplify it as simple as possible. The Rayleigh scattering, that means once that light enters into the atmosphere, due to the air molecules, how much light scatters, we can able to quantify it. That one we are calling it as a Rayleigh scattering coefficient. So that how much light is scattering means, this one we are calling it as a molecular, okay. So this one is the Rayleigh coefficient, 0.008735 into 10 to the power of -4, okay. This one, and that means wavelength, okay. If blue light enters, okay, green light, if it is a blue light enters, then lambda place we can put it a 400 or 450 nanometers, 480 nanometers, whatever the wavelength you have, you can put it here, you can able to measure it, okay. So it's a fourth power of straight away we can able to quantify it. So now if you see that blue light wavelength, okay, 400 to 500 I mentioned blue light, that middle of that one 450 nanometers, Rayleigh scattering coefficient, if you calculate with this equation, is a 0.2271. Red light 650 nanometers. If you substitute this one into this wavelength, Rayleigh coefficient, okay, 0.0507. That means what? Okay. So this is the bigger value, only that 0.02 percentage. If you see this one is a substitute, is this one multiply with 100 is in a 2.2, it will, okay, 22% it will come. If it is come only 5%. So that means what? If blue light 450 nanometers enters into the atmosphere due to the air molecules, maximum light it is scattering. That's why I mentioned during the time, short waves scatters more. So this is the one, blue light, short wave. Red light, okay, less scattering takes place. Okay. So for this one live example, everyone is a general knowledge question. Why during the sunrise and sunset time, okay, sky looks a yellow or reddish, red color. And why noon time, sky looks like a blue color. Only the difference is, once that sunlight enters into the atmosphere, all wavelength scatters. Blue light scatters, green light scatters, and red light scatters. But thing is, during the sunrise and sunset time, the distance between the earth and sun, it's more. That's why whatever the scattered light, blue light, green light, and all the shorter wavelengths, unable to come up to the earth, our eye. Only red light having a more wavelength. That's why it can able to travel long distances. That's why up to our eye, red light only reaching during the sunrise and sunset time. Remaining lights also, it's not coming up to our eye because of that distance more. But if we come to the noon time, the distance is reducing. So, but during that time, whatever the blue light scatters, so all the scattering light in the atmosphere, That's why all sky looks like a blue color. Remaining light, it comes to our eye. Okay, that is the concept. It's clear. The distance only plays the scattering. That's why if you see the traffic signal, why we are using the red light? Red light can able to travel more distance compared with the other lights. Before red light, they are using the orange light. Orange is the combination near to the red. That's why it's a lesser distance it travels. But okay, for danger, wherever the danger, why we are using red light means, if other than red light you are using, it scatters more in the atmosphere. It unable to travel a long distances. That's why within the visible region, whatever the wavelength is, the long wavelength, those long wavelength only we are using as a danger signals. It can travel long distances. That is the concept. I hope everyone understood. Okay? The same way it applies. Okay. So now this is the Rayleigh scattering. Straight away we can able to quantify it. So why we are discussing all these things now? Ocean remote sensing, ocean color remote sensing, we are performing the atmosphere. Any satellite data, we are performing the atmospheric correction. That means, along with original signal, lot of noise entering into the sensor. So if you want to thoroughly, perfectly study this remote sensing data, we should eliminate or remove the atmospheric contribution. How much energy we are going to eliminate in the original signal? Okay, so we should know how much atmosphere is contributing. To quantify that atmospheric noise, we should know this one. These are the scattering phenomena we have to understand. That's why I am explaining this is a due to air molecules Rayleigh scattering. Straight away we can able to quantify it. And now the mice scattering, the molecular size. The mice scattering is dependent upon again the molecular size of the one. Okay, so that means diameter or radius. The radius of the molecule, okay, dust, okay, are pollutants, dust, okay. Aerosols means it may be dust, pollutants, or smoke, or ocean spray, and salt particles and water vapor molecules. Whatever it may, all these we are calling it as a aerosols. Okay. So if aerosol size, okay, if it is a greater than the molecular size is greater than the equal or greater than the wavelength. So that mice scattering, we are calling it as a mice scattering. The mice scattering is a little bit complex compared with the Rayleigh scattering. The equation of mice scattering is 0.08735 into lambda to the power of minus 1.3. Previous case minus 1.4. That means Rayleigh scattering more dependent on the wavelength. So if you come to the mice scattering, it's a less dependent on the wavelength. That means in a previous case, if you know the wavelength, straight away we can compute. But in the here, less dependent on the wavelength, only minus 1.3. That's why the estimation of the Rayleigh scattering, it's a very difficult. That's why different procedures are there. Later in ocean color remote sensing time, I will explain this one. Okay. So these are the foundation of those studies. Okay. So this is the Rayleigh scattering, mice scattering, most of the energy is forward. Okay. So that finally it goes into the sensor after Rayleigh scattering also, but lot of noise involves in that one. Okay. 95% of the scattered EMI continue the forward direction, 5% scattered back. That means, if it is back scattering means, whatever the energy back scattering means, completely it is losing. But this forward, it goes up to the sensor, but it a lot of noise involves in this one. That noise we can able to eliminate it. Okay. So after that, third one is the non-selective scattering. Non-selective scattering means it's a clouds. So that means we don't know which direction it is going. Okay. So that means it's a almost less dependent on wavelength. That means whatever the wavelength, it scatters equally. That's why if combination of white color, why clouds looks like a white color means white color is the combination of three colors, blue, green, red. You mix equally, you can able to see that white color. So that means all blue wavelength or whatever the green wavelength and red wavelength, all are scattered the same. So that's why the clouds looks like a white color. But thing is, clouds are not always white. So when the clouds are white color, clouds contains the ice crystals. If you see this one, any light falls on a ice color also white. Why means all wavelengths scatters similarly. That's why whatever the energy we captures, so we are unable to get proper information from the white things. Okay, so visible, especially in terms of visible light. Okay, so why the clouds are white color means in a form of crystal, that ice form, we can able to see the color of the clouds are white. But sometimes we are seeing the clouds in a dark color. When we are seeing the dark color, just you imagine, just before going to rain, the clouds, if you see this one, looks like a dark. Why before going to this one is there? If it is a white color, the water vapor in a crystal form, water. But just before raining, the crystal ice converts into the water. Water means again it's a transparent. Whatever light falls on this one, it transmits to another direction. That means it is not reaching to our eye. It is going in another direction, whatever the sunlight. Okay, that's why the transmission, wherever the transmission takes place, the clouds look like a dark. Okay, just before going to rain. That's all. Okay, non-select scatter. That's why in especially visible remote sensing, clouds are the obstacles. Under the cloud, if cloud is there, whatever the reflected energy, it never goes into the sensor. That's why under the cloud, simply we are considering masking it. That's why cloudy days, whatever the remote sensing information, more especially in a visible region and a thermal region. Later I am going to explain that one. Okay, so we won't get any real information. That's all. Okay, whatever the sunlight falls on a clouds, it reflects back. That's all. Okay, so that is the one. That's why clouds is there. It's very difficult to operate remote sensing. To avoid this one, we are using the microwave. Microwave is very long, 1 millimeter to the 1 meter. So that's why there is no atmospheric influence there. If you go back, that just you recollect it. After that, that presentation is available on it. You see that classification table. If wavelength is increasing, atmospheric noise is reducing. That's all. Okay. So this is the scattering. I hope everyone understand this scattering. Okay. So now if you see the picture of this one, okay, so 100 units, okay, coming from the sun, straight away 51% absorbed by the earth, okay, from the earth, okay, out of this 151% absorbed by the earth, 19% absorbed by the molecules, atmospheric molecules, okay. From the ground, reflection takes place only 4 units, 4%. From this 4% only, we are performing the earth application. So in this earth applications, land applications are there, ocean applications are there. Especially that's land, other than the ocean, water bodies, non-transparent, 4% signal we are getting through sensor. With that 4% only, we are performing the all remote sensing applications. But if you come to the transparent water body, it's less than 4% because of the transmittance. Okay, well, so that's why water remote sensing or ocean remote sensing, it's very difficult. Very less energy only we are capturing through sensor. With that less energy, we are performing lot of applications. Okay. Now, if you come to the clouds, if anyone is studying the atmospheric clouds, they are having a lot of 20% of the signal. From the atmospheric okay, gases, okay, 6% is there. Total for atmospheric studies, 26% is there. Okay, albedo. Okay, but thing is here, if you come to the land, okay, and ocean applications, very less signal. So that less signal, within that less signal itself, we are performing the remote sensing applications. Okay, this is the one. Now we will go for the after that, how much we studied through scattering, atmospheric is influencing, absorption takes place and scattering takes place. So finally, overall this impact, how much atmosphere is impacting in different wavelengths. So if you consider this one, now you see this, don't confuse it, just I'm simplifying these graphs. Okay, so this is the x-axis again, wavelength. So y-axis represents how much energy is emitting or reflecting. Okay, so if it is reflecting means sunlight reflects, emitting means based on the body temperature it emits energy. Both are same. Okay, so phenomena is different. That's all. Okay, so now if you see this one, from complete gamma rays to the microwaves. If you consider this one, this top portion, if you see this one, transmission. Transmission means how much percentage of energy transmitting. That means atmospheric influence is less. What wavelength the atmospheric influence is less, what wavelength the atmospheric influence is more. That only it gives. Okay. Now, if you see this one, visible light, maximum up to 90%, it goes up to the sensor level. Okay. After that, the infrared region also. Okay. Little bit. Okay. Transmitting. Now, if you come to the thermal, okay, most of the thing is absorbed, okay, affecting this one, okay. But in a thermal region, if you see this one, 10 to 100 micrometers, na. So with this here at this portion, okay, so the small portion, about 10 micrometers, maximum transmission takes place. At this place, wherever at this place, atmospheric absorption takes place. Here in a thermal region, at this portion, absorption takes place. That means there is no transmission at all. Okay, here only 50% only in between. Okay, but here in this portion completely atmospheric absorption takes place. But if you come to the microwave, 100% it goes up to the sensor. So based on the atmospheric behavior, now if you come to the atmospheric gases, for example, if you want to study the nitrogen N2O gases, nitrous oxide, okay, these absorption wavelengths bands are these are that. Okay, so this is absorption. These are the absorption. These are the transmission. Okay, so absorption. If absorption is more, less transmission. That's all. Okay, less transmission. Okay, if nitrous gas, at what wavelength the absorption takes place? So say 2 to 10 micrometers. Then this one is the methane gas at particular wavelengths. Okay, so O3 and this means ozone. These particular wavelengths, like the water vapor in a thermal region, carbon dioxide in a thermal region. So that's why in a thermal remote sensing, the gases only plays a role. Okay, during that time again we will discuss. This is the foundation of this one. Okay, based on the atmospheric property, that atmospheric influence. Okay, remote sensing data we are classified into 3 groups. Okay. So visible remote sensing, this visible remote sensing involves visible light and infrared, okay, near infrared. This one we are calling it as a reflected remote sensing, thermal remote sensing and microwave. That means here the one word comes into the picture, remote sensing, atmospheric windows. Window means normally our home window. What purpose we are keeping windows? Window, it allows air and light. That's all. If any air is coming force, okay, if sun is shining, then immediately we are telling to close the windows. Okay, that means we are stopping it, that one. Okay, so atmospheric window means at what wavelength region atmosphere is acting like a window. That means it's not stopping, it is allowing up to the sensor. What light is allowing? Total electromagnetic spectrum it is not allowing. Some particular portion, regions only it is allowing. What are those portions? Are visible and infrared. Okay, so that is the whatever that particular wavelength reflection takes place. This is only daytime possible. Okay, sunlight incident and reflected light. Okay, if you come to the thermal is only that emission. Based on the body temperature, it emits some energy. The thermal region, some portion of the thermal region, atmosphere acts as a window. That means it is allowing up to the sensor. Those wavelength bands only we are using in a thermal remote sensing. Those are the plus or minus 2. This one is the 8. Okay. So 11, 10 plus or minus means, okay, 10 micrometers is this one. 11 temperature estimation purpose. We are using 11.5 and 12.5 micrometers we are using in the water temperature estimation purpose. Land estimation, the land temperatures at 10 micrometers we are using. Okay, why also during the thermal remote sensing. So in this total course, after completing these fundamentals, okay, we divided okay, remote sensing. Already I mentioned earth applications. So total earth application, land, ocean and atmosphere. In this course, we are dealing only the ocean remote sensing only. This ocean remote sensing, we are classified into 3 kinds of this one. Okay, ocean color remote sensing, thermal remote sensing and microwave remote sensing. Okay, these are the 3 classes. Okay, if you come to this one, without any atmospheric influence, if you want to measure the exact target information, people are opting the microwave. So, but in every case, advantages are there, disadvantages are there. What are the advantages of visible remote sensing and infrared remote sensing, reflect remote sensing? Is there? This is operational in a daytime, and these are the short waves. Most valuable information. That's the energy is more, more very good information it captures. Even though the shorter wavelengths scatters more, but long, whatever the long waves are there, green and red, it carries very good information. Similarly, thermal, it gives the temperature of the information. Okay, it measures of the through it passes the best signal, whatever the signal, particular wavelength bands, it is reaching up to the sensor with minimal atmospheric noise. And if you microwaves, 100% it reaches. But what are the drawbacks and all that? Particular topic thoroughly we are going to discuss this one. What are the advantages and disadvantages? But if you come to this one, thermal is a purely the emission based on body temperature. Okay, daytime it is possible and nighttime also it is possible. And microwaves, so anytime. Okay, even the cloudy days, non-cloud. But in a remote sensing, thermal remote sensing, cloudy days it is not possible. But in a microwave remote sensing, that cloudy days also it is possible. So all weather conditions, microwaves will function. Non-cloudy days, thermal remote sensing works properly, and non-cloudy days, non-atmosphere case, ideal case only, this visual remote sensing works properly. Otherwise, atmospheric noise is involved. This one, this is daytime only. This is day and night. Non-cloudy days, this is day and night. In all weather situations, microwaves will work. So, based on the atmospheric windows, remote sensing data we are classified into these three classes. Okay. Now, if you come to the energy sources, okay, based on the energy source, remote sensing we are classified into another separate classification. What is that classification? Is this one is a passive remote sensing and active remote sensing. That is based on the energy sources. Okay, passive remote sensing means the source of energy. That means incident energy is the natural source. That is the example is the sunlight. This is the one. Sunlight falls on a target, reflected light goes into the sensor. And at the same time, based on the body temperature, it emits radiation. That emitted light, we are capturing it. Both the cases, here incident light is a natural sunlight. Here, based on the body temperature, it emits that radiation. This one is a emitted remote sensing. These two kinds, we are calling it as a passive remote sensing. So that's why the passive remote sensing, further classification is a reflected remote sensing and emitted remote sensing. And reflected remote sensing, only visible wavelength and IR we are using. And emitted remote sensing, that whatever that is emission based on the body temperatures, two ways. Okay, at thermal region it is emitting, and as well as microwave region also it is emitting. So if you capture microwave region, all weather conditions we can able to measure the target temperatures. So if you consider the thermal region, non-cloudy days only it is possible. Okay, all this is the passive remote sensing. So now active remote sensing. Active remote sensing means through microwaves only is possible. From the sensor, where the sensor, we are keeping one energy produce this one. It produces the microwave. That microwave light we are sending to the ground. That light hitting the target, and after that reflected light again it comes to the sensor. We are measuring it 100% perfectly. We are measuring it. So it's an active microwave. Based on the energy source, this is the classification. Based on the atmosphere, okay, we are classified data into three groups. This is the basics of the remote sensing. So with this one, okay, today I'm going to stop it here. So okay, tomorrow, very most important, sensor specifications. Okay, what are the specifications? Means just for example, if you want to buy any laptop, if you want to buy any mobile phone, we are seeing the specifications. Based on the specifications only, we are selecting. Okay, laptop 4 GB is sufficient or 8 GB is sufficient. What kind of processor is required? What is the screen size? How these specifications are there. Similarly, during the designing of the sensor, Okay, each sensor is having a different specifications. If you understand that these 4 specifications, okay, so you can able to choose yourself what kind of satellite data is required for your applications. So that's why tomorrow, first session, within the 2-hour sessions, so I am going to cover the spectral resolutions. After that, ocean color basics, I will cover this one. After, third day, our colleague Anish is going to take the ocean color thorough remote sensing. There he is going to show you better elaboration of this one. Before going to that one, the foundation thing, that basics I will explain tomorrow. Okay, this resolutions and ocean color remote sensing tomorrow we will discuss. With this one, okay, I am going to stop with this one. If you have any questions, okay, now you can post into a chat box. I will answer. Okay, already previously if you pasted also, now okay, again you paste it, I will answer this one. Sir, please explain the terminology of surface reflectance and remote sensing reflectance. Okay, so I hope, okay, Mohammed Rahman, if you are not clear, just you ping it. Okay, sir, please share the more examples of passive emitted and microwave. Yeah, definitely this passive remote sensing during the applications time, so these are the just only fundamentals we are going. Okay, so during the ocean color remote sensing and during the ocean color remote sensing, we are going to explain all these things, what is passive and active things, and thermal remote sensing also during that time, and microwaves. Another continuous sessions are there in this week. During that time, we will stress more on that one. Okay. So now that what is the reflection and what is the reflectance? Simple. Reflection means just okay. I will go back again. Yeah. This is the This is the reflection means incident light. This is the reflected signal. So reflected means if you capture this one, okay, in a one particular direction, based on the definition, that table you see, this one is a one particular direction. Whatever the energy our eye is capturing, that is the radiance. Okay, reflected radiance. So that one reflected light, you divide with incident energy, irradiance. Then it is going to call it as a reflected light. Reflection and reflected, you divide it. Just this one, you see. Yeah, this one you see. Reflected light by incident light is nothing but a reflectance. That's all. Is a one particular direction. Whatever the energy our eye is capturing, that is the radiance. Under any water body, there is a ground. So that's one reflected light. Okay. You divide with incident tomorrow energy. We are going to discuss about the bottom. Then we are going to call it as a. So after transmission, reflected bottom reflectance, reflection and reflected. You divide using that one only. Some of the studies carrying the reflected light by incident light using the ocean color. Tomorrow we are going to discuss this one. Okay, that's all. Is a one particular direction. Whatever the energy our eye is capturing, any question? That is the radiance. No problem. Again, you refresh this one. Okay. Tomorrow we can post the questions. Tomorrow also I will. Tomorrow we are going to discuss about the bottom. With this one I am going to stop with this. So after transmission, thank you everyone. Bottom reflection and reflected. You divide using that one only. Some of the